Hi everyone, this is Will. Welcome to the 23rd miniKanren hangout. Got a slight change of venue. I switched from my desk to my couch because my chair is not very comfortable. Got a couple of cool things to show you. First of all, yeah, Igor, can you hold that up? We got a lambda XX tattoo, so we got lambda calculus tattoo. Very nice. And yeah, oh yeah, so I can't help but show now. All right, so here's the tattoo I guess I could get. Let's see. So Celeste Hollenbeck at Utah has come up with she came up with a logo she was proposing for a miniKanren logo. So I'm just curious what people think about this. Let me bring it up here. Sort of metaphorically, we have at least a metaphorical logo, right? Which is we talked about this before, that Dov Gabay compared logic programming because you have like resolution theorem proving based on unification. So you have this one big hammer and that's it. And he compared it to a fine woodworker building a guitar or something like that. And the only tool that the woodworker has is a rotary saw attached to the ceiling, right? And we talked about having, because we have constraints, maybe having a Dremel attached to the ceiling. So metaphorically, I guess that's our logo. But the ceiling-mounted rotary saw, that's right. So if anyone knows how to draw a ceiling-mounted rotary saw, I think that's a very good logo. I challenged Celeste to draw it, and that's not what she came up with. So let me bring that up, and yeah, let me open that as a preview. All right, I kind of like the rotary saw idea. I don't know how easy that is to pull up as a logo, but let me show you this icon and see what you think. Oops. All right. Here it is. So I guess the idea here is, of course, we have lambda, like Igor said too, but I think the idea is that we're reflecting lambda, so it's like a lambda running backwards. And I've seen, reflected lambdas, but this one forms a heart. So, so love miniKanren or something like that. I don't know. I mean, I guess if it had a ceiling-mounted rotary saw above it, maybe I'd like it more. But it's I like the yeah, it is a very cute logo. I agree with that. Yes, that's true. Daniel points out it goes with a million ways to say I love you. So it's a very cute logo. I agree with that. So the question I had was, are there existing logos that are already like this? So Clojure has a logo with lambdas. Haskell has a logo with lambdas. Lots of languages have lambda-based logos. I haven't seen anything that quite looks like this before, but I was just curious if anyone knew. So that is a cute logo. I'm not sure what Dan or Jason or anyone else or what Oleg think about it, but it's got a cuteness factor. So does anyone know of any logos that are kind of similar to this? Someone must have made a heart with lambdas before, you'd think, right? But maybe not. I don't know. And even if they did, I don't know if there's like a language icon. So anyway, so that's a proposed logo. I don't know how you fit the rotary saw into that though. So I told Celeste I would share it with people and see what they think. If anyone can draw a rotary saw on the ceiling, I would be very interested in seeing that logo as well. Okay. So one thing I wanted to share from last time. So last time we had this long discussion with Raja about different representations of numbers and how to make, Raja he wanted to make miniKanren search biased in an interesting way, where he wanted to say, like, here's an answer I care about, somehow compile the search or rewrite the search so that this answer will come up early, or answers that look like that will come up early, right? So we talked a little bit about that and how you might do that. But he was partly interested in doing this by this task of trying to create numbers and representing numbers as lists and all that stuff. So John Hollick, who's someone at Utah who's very interested in logic, saw that hangout. So I meet with him like every other week and we talk logic stuff. He knows a lot about various types of logic, especially like modal logics and things like that, which frankly I know nothing about, but I'm interested in learning about. He pointed me to this bracket number notation, and this is Leroy Eide talked about this, and anyway, I'll put a link in chat and I'll put it on the YouTube video, but you can see that it's got representations of numbers that are very similar to what Raja was playing around with. And it's got all these interesting representations of numbers. So I thought that might be interesting to Raja or to anyone else who found these ideas. Different number of representations are always interesting, especially for once you get into the relational stuff, right? So anyway, he pointed out that list-based representation of numbers looked very similar to what Leroy Eide had proposed before. And there may be other representations as well. In fact, I think, Greg, you've talked about different representations of numbers also, I think, in some of our emails. Okay, so without further ado, okay, so let me tell you what the plan is. The delayed carry binary, yeah. So we've got lots of things to talk about today. Should be very interesting. We have a first-time visitor, Greg Rosenblatt, who I've been chatting with quite a bit on email. And Greg has lots of interesting ideas and questions about miniKanren and logic programming and things related to logic programming. And I think he's going to show us something cool today that's not miniKanren, but that is very much in the logic programming vein. I'm very excited to see this. And based on our emails alone, we could spend multiple hangouts just talking about the things we talked about in our emails. The other thing I'd like to talk about today is trying to make the relational interpreter that we've spent so much time on, try and look at that and understand what the performance is and how we might make it faster. And in particular, approaches to specializing the interpreter, sort of doing some hand specialization or automated specialization. I was playing around with that a little bit yesterday, and I've got some interesting versions of the interpreter that I'd like to show you or play around with, and we can look at some of the things I was trying, and they're pretty naive, and I'm sure folks in the Hangout will have much better ideas of how to optimize things. But it was interesting just to see how these little tweaks worked and what worked and what didn't make a difference and so forth. So, basically the bottom line is when running forward, when running append with everything fully ground in the relational interpreter, append runs like at least 30,000 times slower than an equivalent scheme version, and it takes at least 100,000 times as much memory, which isn't great. Right? I mean, when it's fully ground, you would hope that you could compile it or specialize it so it runs almost as fast, maybe not quite as fast as in Scheme, but at least as fast as Appendo. Appendo is also actually much faster than I had realized, especially if you use efficient data structures to represent the substitution. So if you run these programs in Veneer, which David Kahn's version of miniKanren that runs on the web in JavaScript, it's surprising. Well, it's not really surprising. I mean, I know this, but it turns out good data structures matter. And some things that we're running in microKarren, which is that's pretty smart scheme compiler. But if you use a version of miniKanren that doesn't have smart data structures, things run really slowly. And as soon as you switch to an implementation uses a smarter representation of substitutions, things get way, way faster. So I was able to run things way faster in Veneer than in Vicari. Because, to be fair to Vicari, the version of miniKanren I was using wasn't as smart because, as far as I know, Vicari doesn't have built-in persistent hash maps and things like that. Although there is a persistent try implementation that Aziz Galloum created that I want to try to integrate back into everything. Anyway, so that's also lots of fun to play around with, and I'd be very curious to see what ideas people have for making things faster, because honestly, it's kind of ridiculous to be using 100,000 times as much memory for no reason. So anyway, okay. So let's begin by going to Greg, and why don't you go ahead and show us whatever you want to show us? I guess you're starting up with your miniCurry, right?
Yeah, I'll probably bumble through it a bit because I didn't actually form a good presentation, but hopefully you guys can drive it a bit with questions.
All right, I'm sure we can. Oh yeah, I should also mention that Greg is quite the expert in Go, not the programming language Go, but in the board game Go. So what are you, 5 Dan?
Yeah,
Wow.
According to the A.K.A, sure.
I am.
I don't know if I actually am anymore because I haven't played in a long time, but yeah.
I am not 5 Dan. I'll just leave it at that. I did play Rich Hickey recently, who's quite good, and he gave me a lot of good pointers. So I'm starting to try to get back into it a little more. But if you've never played Go, that's a great game. Okay. All right, so tell us about miniCurry, please.
Right, so actually, let me share another link first so that you can see sort of what I'm attempting to emulate. So
Okay.
here are a bunch of examples of functional logic programs written in Curry. So Curry is a functional logic programming language that's very similar to Haskell, but you can also run programs backwards because it includes logical operators similar to miniKanren. So I've written an interpreter for this miniCurry-like language on top of microKanren. It uses the same conjunction. Well, it uses a variant of the conjunction and disjunction operators that includes a concurrent conjunction, so that rather than evaluating goals one after the other, goals that are codependent can be evaluated at the same time, so that if one contributes information that the other can use to cut off search early, then the whole thing will be able to cut off search no matter what the order is that you specify these conjunction terms. Did that make any sense?
All right, what do people think? Is that...
So, for instance, using appendo as an example, there's this this problem in normal. Let me find it. So in normal miniKanren, you cannot write appendo in this way because if you do, then run star will run forever if you try to run it backwards. Is that familiar to everyone?
Yeah, and in particular, it's when the first argument is fresh, I believe, and the other two arguments are ground, then run star will diverge, is one example.
Right. So with concurrent conjunction, you can actually run write these in either order because both goals are going to be executed at the same time, and eventually the information from the second clause will arrive in time to cut off the search for the first one when there are no more answers.
So can you actually express appendo like this in your miniCurry?
Yeah, of course. So actually I can express it in my version of miniKanren as well. This is miniKanren, by the way. Implemented on top of my version of microKanren. So I could show what that looks like briefly. Sure. So I've changed the search algorithm that previously was using m plus and m bind, and normal bind from the original presentation to construct this kind of evaluator that takes, let me get to the, right, so this is what a computation looks like now. So there are two different versions of conjunction. One is has the same semantics as the original, and the other is the new Curry-like concurrent conjunction, which allows both clauses to be run simultaneously. And disjunctions are basically the same as before. But the idea is that computations are these trees, which they can be arbitrarily nested conjunction or disjunction terms. And yeah, other than showing this code, I can try to step through examples, but I'm not sure that I can say anything more meaningful than my high-level description.
Okay, so let me see if I can understand this. Okay, so one thing, if you have two types of conjunction, you have the concurrent conjunction and the sequential conjunction. Does the user of miniKanren or whatever, or Curry, have to explicitly say which conjunction they want, or does the system figure it out somehow?
So by default, the system chooses concurrent conjunction for you unless you specify that you want to use a sequential conjunction for, say, optimization purposes.
Okay, I see. So sequential is just an optimization case. Okay.
That's right. And
if you're always using concurrent conjunction, is this equivalent to something like a breadth-first search, or is it actually different?
So by default, it will be a breadth-first search, but I actually have this this depth parameter, which describes how far to go down a specific branch before coming back up for air and trying another one. So you actually have iterative deepening here available as well. And actually, if you set the depth parameter to -1, you get depth first search. So.
Okay. And is there a default depth for that?
So the depth by default is defined in my miniKanren implementation of run, which is set to 1, I believe.
Okay, so at a depth of 1, it would be like breadth first search. Is that right?
Right. So in that case, it would behave like breadth first search. So.
Okay.
So I have these additional operators, run depth and run star depth, which allow you to actually specify the depth inside of a run clause. But the normal definitions, these guys, they set depth to 1.
Okay. And
actually, this is a mistake.
All right. So can you show this in action? Can we play around with some tests?
Yeah, sure. So I would probably do it through miniCurry, though, unless you actually want to see me do boring miniKanren stuff that you've already seen, because it's not really going to behave that much differently, other than you can switch the lines of appendo and it still works.
Sure. Well, I guess the thing I'd be curious about is that we've implemented breadth first search a few times, and we found that with the relational interpreter, for example, in practice, we're not able to generate the bigger terms because it just takes too long to get there. And I was just curious if you've had any experience with trying to generate larger terms and deeper terms, and if so, do you have to either go in and make things sequential in practice, or do you have to tweak the depth parameter in order to get larger terms? Do you have any experience? Have you played around with that at all?
So I guess the largest example I've played with is the send more money thing.
Okay.
Which I've commented out because it's really slow.
Okay.
So I've kind of hand optimized it to try to get it into a situation where I can actually complete a run in a reasonable amount of time. But as you see, I couldn't even put a single query variable to represent the entire result. I kind of had to hand pick these guys. I think 6 is the most I've been able to do without losing patience. But,
and your depth is pretty deep, right? You're going 4,000, is that right?
Oh, right. Yeah, so I noticed that on some problems, different depths return answers more quickly. Here, I think 4,000 ended up being the optimal case.
So
yeah, it's something that you can hand to.
So one place where I could see using this is in the tricky part for miniKanren. I mean, obviously, if you understand miniKanren at all, you know that you can reorder the unifications to come before the recursive goals. However,
Right.
the tricky part isn't so much append. The tricky part is the case where you have two recursive goals in the same conjunction, right? And then you really do want probably something more like a binary, like a concurrent conjunction in that case. So I'd be curious if you could take something like the relational interpreter, where cons has multiple recursive goals, procedure application has multiple recursive calls, that kind of thing, and sequentialize all the rest of it, and then see if you would get any benefit there. I'd be curious to see if that would be possible.
Yeah, I could definitely see that being plausible. Because the concurrent conjunction is designed to be able to allow codependent recursive invocations to help each other as they go.
Yeah, and so a typical example is cons, where you're consing E1 onto E2, where those are logic variables representing expressions. And if you're consing 3 onto E2, and the output value is the pair 4.v2, then it's not consistent and you can immediately fail, right? So the relational interpreter will fail. However, if you swap the order and you say you're consing E1 onto 3 and the output value is v1.4, in our standard relational interpreter, that will go into an infinite loop, because we're the search in a conjunction is happening in this biased way where the first conjunct wins. So I could see this as a potentially a big win, although you do have this exponential explosion, I guess, once you start going deep into recursion.
Right.
Okay.
So that probably links a bit to miniCurry, and I could see that it's possible that miniCurry could sort of behave like an optimized version of the relational interpreter in special cases where you don't actually have to replace code with query variables. And the concurrent conjunction does seem to be working pretty well there. I haven't actually run any benchmarks, but for instance, running append backwards is quite fast, just like in miniKanren, so it doesn't seem like there's any noticeable overhead.
Good.
So I can explain how that works.
Sure, but before you go on, Daniel had a question.
Sure. Oh,
is there?
I wasn't watching.
Is it? Yeah, I'm happy to read out the question to you. Is there a notion of the complexity of a goal to help control convergence through ordering? This is, I guess, okay, Daniel is asking, is this more of a general question for miniKanren? Right. Yeah, that's a good question. Right now, we don't have anything like that. I've been thinking about it, either from a standpoint of abstract interpretation or user annotations or runtime groundness tests, things like that. In fact, that's going to get into some of the things I'm going to show later in the Hangout. That's one thing I'd like to be able to do is in that cons example, if you see that one of the arguments is ground, you want to do the recursion on that argument. That sub expression of cons. You want to recur on that before you would recur on something with a variable. Yeah, Greg's asking, R-Kanren has a form of code annotation that allows you to control this a bit, more for disjunctions. Yeah, so we talked a little bit about R-Kanren last time. It does give you some control with some biasing. I'm not sure if that's the level of control you want. I think with the cons example, for example, what you really want to do is the recursive calls in the cons should be controlled by the groundness of the arguments to some extent. So if you're consing E1 on the E2 and you have to recur on E1 and you have to recur on E2, if E1 is fully ground, you want to recur on that first. If E2 is fully ground but E1 is not, you want to recur on that first. If E1 is more ground than E2, basically you want to say if one of those two expressions is more ground, has more structure, that's the one you want to recur on first, if possible. If neither one is really ground, though, maybe something like the concurrent conjunction is what you really want, even if that's going to potentially give you, that could be expensive, but it's less expensive than an infinite loop, right? Daniel says, I just wonder if we could come up with some sort of equivalent for big O notation for different goals. In some sort of formula automated way, perhaps formulated in terms of unification, this could provide a way of manipulating clause order at runtime. Okay, so that's a very good point, and I know of some work in this area. There's been work in Chow Prolog where you can put annotations on your goals with the big O running time, and the Chow Prolog compiler will take that into account for parallelization. So there is for parallelization. I don't think it's for goal ordering, but you could also imagine doing something like that for goal ordering as well. And there's also been work in functional programming to automatically do this, not require program annotation. I know A.K.A has done work in this area, for example. I think there's a long history of work in this area. But yeah, we're not taking advantage of any of that. And I also think things like abstract interpretation would be very useful. So the stuff I'm going to show you today is sort of my first attempts at trying to play around with looking at the runtime values to try to make the interpreter faster in some cases based on runtime values. But what I'm doing is pretty crude, and it could be pushed a lot further, I think. Okay, good questions. All right, Greg, do you want to show us a little of your miniCurry action?
Sure. So, like I was saying before, it's a functional language that so normal curry is a functional language that's very similar to Haskell, but also includes logical operations that are similar to miniKanren. So miniCurry is just an attempt to emulate this somewhat on top of microKanren in a way that is compatible with miniKanren, so you can run miniCurry invocations side by side with other miniKanren programs.
So when I think of things like Haskell, I think of the type system and laziness and things like that. I assume as miniCurry is just going to be dynamically typed like Scheme and.
That's right. It's a bit more like Scheme than Curry is like Haskell. In addition, it's dynamically typed, and there is a form of laziness though that's sort of simulated by the concurrent conjunction. It's not truly lazy in the same way, I don't think, but it does do the job. So a lot of things that you could write in Haskell, you can write in miniCurry, even though it's not really doing the same thing. So I can show some examples. So
yeah, please.
miniCurry defines this. It defines this. I think it is. I think you can accurately call it a denotational interpreter. So it takes syntax and builds scheme functions to represent the computation. So it's not really compilation, but it's transforming the representation into primitive directly to racket functions. So it's based on this function called denote, which takes the syntax, does this analysis, kind of like you would see in the relational interpreter. I haven't looked at it that closely, but it does a case analysis, and based on each of these cases, there's a function that determines how to transform this into a function that takes an environment and produces a goal that can be run in miniKanren. So I guess if I would write the type of denote, it would look like this. So it takes syntax and produces a function that takes an environment that, given the environment, produces a goal. And the goal is just like the normal the normal miniKanren thing, where it takes a miniKanren state, which either it's a substitution or some combination of substitution and constraint store, etc. And it produces a headache. Sorry, I mean a stream of states, right?
Yes. Or a headache.
All right. So this is the structure of denote. So I actually built this originally as a normal reference interpreter for a non-logical language, where the type was analogous to the value in this case.
Okay. I think Google Hangouts is auto-muting you because of your keyboard, by the way.
Oh, okay. Can you hear me now, though?
Yeah.
Okay. So the reference, did you catch that about the reference interpreter?
Can you say that again? So this is for a non-functional language?
Right. So, sorry, this is for a non-logical language.
Oh, sorry,
without the logical operators. Okay. Right. I implemented a plain old interpreter to base this on, and then sort of transform into a functional logical language in a way that I could be sure that I wasn't. When I saw errors, I could sort of trace it back more easily to what I did wrong, rather than scratching my head and saying, "Oh, I don't even know where to start."
Sure.
So I wrote this original reference interpreter where the values are sort of analogous to the goals.
So I'm trying to wrap my head around this a little bit. So you're writing sort of a functional interpreter or kind of a goal compiler that's going to take some expressions that are like miniKanren-ish, like something like that, that express goals and things like that, and it's going to compile them into functions then that take an environment. So you got some sort of like we have these goal constructing expressions. I mean, that's kind of how miniKanren works, right? So equal 5x, that actually produces a function that takes a substitution and returns a stream of substitutions. It's like equal is a goal constructor.
Right, exactly.
But
right,
it
so
feels like now you have instead of having macros and functions, you have an interpreter doing the similar sort of thing. Is that right?
Right. So denote itself is a given an environment. So denote is a goal constructor you can think of.
Hmm.
So denote takes right. So denote sort of behaves in the same way that equal does. Once you give the result an environment, which at the top level is going to be the empty environment. So values. So the thing analogous to the values in the reference interpreter are the same as miniKanren's goals.
And what's the environment? Does that have logic variables in it?
Oh, so the environment is just a normal, it's for lexical scoping. It's just, it starts at the top level, it's empty, and as you go down inside of lambdas, it gathers bindings, right? Okay,
and is that for both regular lexical variables and logic variables, which are also lexical?
So none of the substitution stuff, none of the logical state is involved in the library itself, except that the environment sometimes stores logic variables if they're passed around in query programs like values. So for instance, if I pass a logic variable to a lambda as an argument, the lambda will take that logic variable and distribute it as it needs in its body.
Okay.
So that's the only way that say logic variables end up in the environment.
Gotcha.
Or as part of other data structures.
Sure. Okay. And once again, this is sort of similar to miniKanren because logic variables are just bound to normal lexical scheme variables in miniKanren.
Right. Exactly. So it's the same in that sense.
Yeah. Okay. Cool.
Yeah.
Sorry. Go ahead.
Yep. So I can sort of a breakdown of the special forms that you have available to you in this this mini language. It's basically this pseudo scheme, though it's slightly deranged because I don't have good taste. Plus some logical operators that are very similar to what you have in miniKanren.
So can you do something like generate quines or generate programs that say I love you or things like that?
I haven't actually tried doing that yet.
How hard would that be? I mean, can we do that in real time?
Yeah. It's a good question. Maybe I'll think about it after the first initial demonstration is done. So this is actually very new still. So I've only even first encoded these curry examples just earlier today. So I haven't gotten into any big experiments yet.
So how would you define something like a pen? Like, what would a pen look like in miniCurry?
Right. So let's take a look. So this is a pen in miniCurry currently. So it is this definition right here. It sort of looks like what you would write in Racket. Mm-hmm. So this is actually the way it's not very modular at the moment. The way I'm actually sharing code across invocations of denote eval is by quoting a block of text and then distributing this using unquote splice in these letrec statements. So for instance, this example right here, it's actually running this computation, but it has the shared bindings in scope due to this letrec. So it's not really the best story for modularity at the moment, but this is how I'm doing it. But anyway, you can pretend that these definitions are part of a letrec statement. So this defines a named lambda called append that takes 2 arguments. It does a pattern matching on the first one. When you have a list, when you have an empty list, you just return the last argument. When it's actually a con cell, you take it apart and you build a new list with the head of that and the recursive invocation of append on the tail and the second argument.
So pair is cons in scheme? It would be equivalent to cons. Okay.
Right. So pair is actually a primitive sort of operation here. A first-class function called cons in terms of pair down here.
Gotcha. So that's just your tagged representation of a pair.
Right.
Okay. Okay.
Like I said, it's not really necessarily the best taste, but this is what I started with.
So is pair a value, or is it a user level function? So could you replace the pair with, or would that change? Would it?
Yes, I could. So for instance, if I just do like this, actually the test should still pass.
Okay, so I'm trying to understand. So
sorry, cons, I got muted.
Yeah. So cons produce.
And the test do still pass.
Cons produces a pair. Is that right?
Right. Yeah.
Okay, so by putting pair there, you were basically evaluating the cons by hand. Is that what was going on?
Yeah, sort of. So I can show you how pair is implemented. It's really underneath.
Yeah, you got muted again.
Can you hear me now?
Yeah.
Is there a way to turn off that auto mute?
There is, although I have to kind of look it up. There's some special magic invocation to do that. Yeah. I'll see if I can find it. Although I don't know if it's just a keyboard, because you seem to be muting other times too. I don't know. Well, we'll deal with it. Okay, so
yeah, pair is just defined in terms of the normal scheme cons.
Okay, cool. So can you show us append at work and running backwards and those sorts of things?
of append, let me first note this example, which, so this definition of last, for finding the last element of a list. Now, lambdas actually take patterns as arguments rather than simply just identifiers. So you can actually substitute a normal variable name for a pattern of any kind, either say these simple data patterns like empty list or cons, but also function application patterns. So right here, what I'm
you got muted. So what? So append is itself a pattern?
right. So it supports function application patterns.
So okay, so that's where the laziness comes in. Is that right?
This is one area where the laziness does matter. Yes.
Okay, because you're not going to call append. So say your definition of append for some reason went into an infinite loop, right?
Right.
Yeah.
So, so function applications are lazy in the sense that they spin off a concurrent computation while immediately returning a logic variable that sometime in the future it promises to constrain its result to.
Yeah.
So that you can immediately use that logic variable in the subsequent computation, say as part of a pair structure.
Okay.
So I can show maybe a clearer example of running append backwards. But so this is running pair append forwards. This is running append backwards. So here I've taken the two query variables R and S, stuck them in the argument position, and said that the results of append should be constrained to this list 1, 2, 3, and you get the same miniKanren like result.
Can you do partially instantiated lists?
As arguments?
Yeah.
Yeah, absolutely. So, for instance, I can do, say, this.
Okay, so...
Sorry, my file system's a little slow.
All right, so it's 1.r. Okay. All right, so we're saying 1. Okay, so R is going to be. So R could be like the empty list, right? And in that case, S would be 1, 2, 3. Yeah. Okay.
Right, so in this case you can see a test failure because I changed the behavior. But now the results are missing the initial 1 because I've taken that into account in the partially instantiated argument here. This is what you meant, right?
Yeah, yeah. Okay, so so would you say it's just as general as miniKanren then? You can put logic variables anywhere you want?
Yeah. So it's designed to, so these operations are themselves built on top of the microKanren operations. The only difference is that you also get this functional evaluation mechanism that happens before the logical stuff takes over, or sort of interleaved with it.
Interesting. And so your append, that is basically a function of 2 arguments instead of a relation of 3 arguments, right?
That's right. So the third relational argument is implicitly the result of applying this function.
And you don't have to do any of your unnesting for the recursive call or any of that stuff.
Right. Yeah. So the recursive call, if you look at the definition of append here, this is pretty much what you would write in Scheme, right?
Yeah.
So yeah, the recursive call is just directly embedded inside of the cons.
And can you say something about the performance of it? It's hard for me to tell from the the screen on the right, which I'm not sure I'm looking at the right test. So when you're doing something like running the append backwards, I guess I'm not sure exactly what microKanren code that's turning into.
Yeah. So I can go through the transformation a bit, and
Okay.
that probably will make it clearer.
In terms of performance, if you're just running it backwards, is that saying it's running in a couple of milliseconds, or
it is like a few milliseconds, yeah.
Okay.
Not at the moment because my machine is currently overloaded with the Hangout, but
okay.
usually it's much faster than this.
Okay, gotcha.
I don't have a very powerful machine.
Okay. Well, yeah, I saw 13 seconds. Like, what? Okay.
No,
sure,
normally, so the overhead of running these tests is usually at least around 3 seconds or so, and after that, there is some overhead in doing the transformation of the program. It's only a few hundred milliseconds beyond that for the entire invocation. Okay. Which includes all the examples and all the syntactic transformation and stuff.
Could you write? Well, I'm trying to think of this in terms of like the relational interpreter or something like that. So could you write a scheme interpreter, like an environment passing scheme interpreter, just like you wrote append, sort of like in the straightforward style?
Right. Yeah. So that was going to be one of my my experiments after this. I was going to try to make a self-interpreter too, just to see how well it did.
And do you have you can do higher order functions, right?
Oh yeah. So for instance, here's map and fold and fold L, fold R. Okay. One thing I'll note that was interesting was that functions defined in terms of fold L don't run as well backwards.
Hmm. Okay. And is this something to do with microKanren, or is this a curry thing?
I think it might be just something about the style of accumulator passing. So for instance, if you look at the definition of fold L, the accumulator is buried inside of the recursive call, whereas in fold R, the recursive call happens as an argument to the function that you are folding using. So it's sort of like this will give you structure faster than the fold L will.
Yeah, this looks very similar to the problems we've run into with CPS and things like that, right. Where you'll still fail, but you won't fail as fast as you would in direct style, and that can cause divergence instead of termination, things like that. Yeah, and I ran into similar problems with fold in the past with that sort of thing. Do you know if straight curry would do any better with this? I mean, do they have any tricks to try to get around that?
I haven't actually tried it, but I did notice that on their examples page, they defined reverse in this way, which is the quadratic algorithm.
Oh, okay.
Which is interesting because, yeah, that's the quadratic algorithm. Fold L is the linear time algorithm. I'm wondering why they chose that. Maybe it is because it actually does run better backwards for them as well. But yeah, I would have to try it with curry to see. I haven't done that.
Gotcha.
But yeah, you can define all the higher order functions the same way as you would in Scheme. It's pretty much the same. The only difference is you get to do all these other neat things, like, for instance, this is a computation that constrains, it implicitly constrains a list to contain a certain element. So the way it works is the first argument is the element that you would like to be an element of the second argument's list. So the identifier element appears twice. It appears there. Actually, yeah. So what it's saying is that the second argument is some list that has the structure of appending something to a pair with its first argument being an element, and the tail is the rest of the list. So this suggests that element does actually appear in the list. So member is not actually, so member is a function, but it doesn't actually have any interesting results. So it's actually returning a unit here. Its entire effect is logical. So if this appears in a computation where element is not part of the list, it will immediately cause that branch of the search to fail.
And your append, is that lazier than appendo in a way?
It's only lazier because of the concurrent conjunction. Otherwise, it's basically doing the same thing. I think that the goal that it constructs probably looks a lot like what appendo is in miniKanren. So the function that is actually generated looks very similar.
Orchid says, this is cool. It's like pattern matching, but on code.
Yeah. Which part do you mean?
I guess the fact that you're able to pass around things like calls to append, right?
Yeah.
Evaluate it immediately, but then you're pattern matching on it.
Yeah. I thought that was really cool too. So yeah, what this actually does, I can show you the pattern matcher, but it's kind of ugly. So it might be better to just explain at a high level what it's doing. It's taking these things apart, replacing them with normal lambda arguments, and filling the body with these equal constraints that have the actual application call that appears in this pattern in the argument list of the equal. So it's just doing some rearrangement and then executing something that looks like what you would see in, say, a normal miniKanren program.
What about numbers? Can you handle numbers in any better way?
I haven't implemented any arithmetic yet. You could add, say, primitive operations that take just the flat integers, or that would appear in Scheme, and run the primitive add or other arithmetic operations on them. But in order to do so, in order to be able to handle the logical variables that come in as arguments, you have to pause the computation until they're fully ground.
Gotcha. So a delayed goal type thing.
Right. So for instance, in microKanren, I've added this term called pause, which allows a computation to say, actually, I can't make any more progress until something else happens. So stop executing me for a while. So this is what the...
Oh, go ahead. Igor is asking, can we see an example of what it compiles down to or transforms into?
Right. So I can do so indirectly by showing you sort of the structure of what one of these, what denote actually does. I don't actually generate code that you can see. It's more just implicitly defined.
Because these are going to turn into functions? Is that
right, exactly. So let me try to find, let's see, what is a good example that's really simple to follow? Maybe I'll just show you what lambda does. Actually, let me start at the top. Simple values. So a simple value is actually using the same unit that appears in microKanren, but it takes a result value. So sorry, there are so many things that I've changed that all the explanations kind of get interwoven into each other. So logical states are no longer just substitutions. They also include a computational term. So so the stuff that is appearing in miniKanren, you can think of as having a computational term that is just unit or void or something informationless that doesn't matter. But miniCurry makes use of it in order to pass result values around. So the unit function from microKanren is extended to take one of these result values as a second argument. So this is the normal microKanren state. This is the value. Notation for a sort of an implicitly curried function. So.
Is this a continuation in any way? I mean, are you building up? Are you
Right.
building
So
up computation?
Yeah, it's a little bit like it creates a function expecting a state to be eventually passed to it, right? So in that sense, you're constructing you're constructing a continuation that will eventually receive the logical state and then progress with its own evaluation. So this is this will just be like say Haskell's type notation. I don't know. Where this is sort of like the stream of states that you normally see in miniKanren.
Okay.
But yeah, so this function muck value or miniKanren value is taking a value and returning specifically this sort of continuation type thing. Does that explanation? Is that what you're sort of asking?
Does that help, Igor?
Okay.
Yep.
Yeah. So going back here, this is sort of what I was saying before. All the denotational transformations, they take the syntax and environment and produce something sort of like a continuation here, which expects the logical state streams, the state stream. So where this thing is actually also referred to as a goal.
Cool.
So yeah, that's a very simple case. More interestingly, let's look at, say, denoting a lambda. So actually, let me show you where the source is first. Right. So lambda is a special form, and what this means is that its meaning it comes from this syntactic environment, which I'm also passing around while doing the syntactic to goal transformation. So in the heart of it, this denote with function is doing most of the work. So this case where you actually have a parenthesized form, what this means is we look at the head, and if it is a symbol, then we look in the syntactic environment to see if it has a special meaning. Which is what this case means right here. Then take that special meaning and just invoke it directly to carry out whatever further syntactic transformation it chooses to do. So it makes the interpreter somewhat extensible in the sense that you can add special forms to the syntactic environment, and it will just automatically work with everything else. Application is a special case. When the head doesn't have a special meaning, then you just assume you're doing a function application. So yeah, so lambdas inherit their meaning from this function here, which is actually just invoking a helper function right here, which takes the tail of the form, makes sure it has this kind of structure, and if it does, it attempts to apply the pattern matching transformation that I described earlier. If it succeeds, then you actually end up in this part here, which makes it clear what the structure of the output looks like. Each of these outputs is a function taking an environment and producing one of those goals, just like I showed you muck value constructed before. So muck value takes a value, in this case, a literal racket lambda, which represents the actual procedure that will eventually be applied to the argument result, to the result of evaluating the argument statement. So this guy right here is going to take its body, give it an environment that has been extended with the value that was computed for its argument, assign that value to the parameter name, and continue its execution. So body itself is a function taking an environment to a goal.
Okay, I think I'm lost in the details now.
Right. Okay. Sorry. There's a lot. There's a lot of sort of indirection going on here. But,
yeah.
So the main driver of the computation, maybe it's better to look at that, is this eval goal cont function. So what this is sort of like a trampoline of some kind that bounces back and forth between the miniCurry world and the miniKanren world.
Okay.
So it takes a continuation, which is it expects an actual honest value that will then. So this is sort of like, okay, what is a good way to describe this? Okay, so continuation takes an argument of some kind and produces a goal. And we can see in the simple case that this is what we're expecting here. So it takes some value and produces a function that expects a state and then produces some result. I'll tell you that it's a stream of states, though. So because it takes a state and produces a stream of states, it's a goal. You can think of the type that way. After it's taken the continuation, it takes a value goal. So it's a goal that promises to compute the value that continuation wants to take. And so we eventually actually look at the goal and see, does it represent a computation that's already done? If it is, then we pass the value to the continuation. Otherwise, is it a sequential conjunction or a concurrent conjunction? If it is, we sort of take the head of that computation and allow ourselves to embed the continuing computation to be embedded inside of it. Let me give a good example of that. So let's say we have a conjunction like this, and we have some miniCurry computation that it is sort of embedding something that has resulted in this. What eval goal cont is going to do is it's going to rewrite this to look like this.
All right, you were muted there for a while.
Oh, sorry. So what eval goal cont is doing is it's sort of rewriting this kind of thing. So if a miniCurry computation is embedding one of these guys, something that results in a conjunction, then it sort of rewrites it to this form. So it allows the computation to continue on B while also running the computation A concurrently. Or sequentially, if that's what you've chosen.
Yeah.
It depends on which case you've ended up in. Otherwise it's a pause, which sort of does what I described before. It says wait until later, or it's a normal goal, in which case you apply the goal to the state to get your stream of states. So sorry, this is sort of my I've kind of butchered Racket a bit with my my syntactic sugar, but this is sort of like almost like a list comprehension. So this is taking each of the elements that come from the state stream. Each of those is a miniKanren state and a computation result, and it continues running with this trampoline with the original current continuation and the subsequent computation. arrived at from evaluating the goal. Sorry, that was a very long-winded explanation. Did anyone follow that?
I followed a little bit.
Okay.
I generally have to look at this code before I really understand it.
Yeah, sorry. There's a whole lot of stuff going on here. It's probably a lot easier to re-implement from scratch than to dissect what I've done and figure it out.
Well, it's very cool what
Has it right. Has it right. Goal constructor constructors.
Yeah, goal constructor constructors. That's right. And is this similar to how Curry itself works?
I haven't looked that deeply into its implementation. I've only looked at its operational semantics, and I don't think this matches exactly what they have, but it's very similar. So, for instance, their state streams do look like this. They have this structure of sort of logical state paired with a computational result.
Hmm. And Curry uses needed narrowing, is that right?
Right. So I can't say that this is needed narrowing, but it simulates it using the concurrency.
And what is narrowing?
So narrowing. So I had trouble finding the definition of this, but once I did, it seems like what miniKanren itself does can be considered narrowing, which is it's not just an undirected search by trying random stuff. It's a search that works by guessing things that are relevant to the current computation.
Okay, so avoiding generating tests basically is what you're trying to do with the needed narrowing. Is that the idea? I mean, how is miniKanren in some senses search is pretty stupid, right? It's we can get some pruning and potentially can prune infinite trees in some cases, right?
Mm-hmm.
But although if you're not very careful, you can enter generate and test land very easily and just do sort of naive exhaustive search. Now it's an iterative sort of interleaving search.
So what needed narrowing does, I think, is it's sort of like narrowing, but it chooses the order in which to evaluate logical computations in a way that makes sense based on the dependencies in the functional program structure itself. So, for instance, thinking in terms of Haskell, when applications are normally produce these lazy thumps that are not evaluated until they're absolutely needed, say when doing a pattern match on them in a case statement. So what I believe needed narrowing does is a similar sort of thing where a goal is not actually executed until the results of a goal is needed to make progress on the functional evaluation itself. So in that sense, it prevents sort of unrestricted search by constraining the invocation of those searches to when the functional program says, okay, I actually need that result now.
So it's sort of like a call by need for this functional logic programming.
Right, I believe so.
Okay. I was thinking about that the other day when I was messing around with the CPS. So we don't do very well with code that's written in continuation passing form because it's the same problem you ran into the fold with the fold, I think, is that you're guessing a value and then you don't know that you guessed the wrong value until the continuation's invoked at the end of the computation. But I was wondering,
right.
I wonder if you were doing this in like a call by name or call by need system, if you would be able to. I don't know. I don't know if you'd be able to. You might end up doing exactly the same thing. I'm not sure.
Yeah, it depends. It's possible that even with the call by need structure, that you wouldn't actually have access to the information you need until the very end anyway. So
yeah,
it might still be the same problem.
Orchid asks, is this related to widening from abstract interpretation? I guess the needed narrowing.
As far as I know, it's different. I think I know what you're talking about, but I don't think it's quite the same thing. I think maybe just the names, the terms like widening and narrowing get overloaded in different contexts.
Okay, so with what you've implemented, since you're running on type of microKanren, uh, I guess at some level you're going to inherit some of the benefits and some of the limitations of microKanren, right? But you have this nice way where you can write things in the pattern matching syntax. It looks very functional, and it's you can write append where you don't have to unnest the recursive call and all that sort of thing. So that's very nice.
Right. That's basically all it is. Yeah.
Yeah. Do you think you can massage this to the point where you could run just like actual scheme code in this as a relational source?
Oh, yeah.
Basically saying, just like we're doing with the relational interpreter right now, sort of one of the nice benefits of it is that it really does. I mean, it's a subset of scheme or racket, and you can just take the code and run it correctly and stuff like that, right?
Yeah, I think you could do something very similar. You just have to sort of change the way I've skimmed the syntax for this. I didn't follow exactly what scheme is, but you could do something very similar just by changing what the syntactic environment binds.
Gotcha. Yeah, it'd be very interesting to see how that works, especially how the performance compared, because, like I was saying at the beginning, the performance of our relational append is not, or append in the relational interpreter is, leaves a lot to be desired.
Yeah.
All right.
All right. Any other questions? Do you want to see more examples, or let's see? I'm not sure there were any other really good ones, but.
Well, I mean, there's only one example I want to see. I want to see relational interpreter for scheme or racket. That's what I want to see first.
Okay, sure.
That's, I'm sort of obsessed with that, I guess. But yeah, I think you could do that. I don't see why you couldn't. What about constraints like absento or disquality constraints, or what about things like representing closures? Do you have a good way of representing closures? So one of the things we've started playing around with is having records. We got Michael Valentine and I, we played around with adding records to our miniKanren so that we could represent closures as records instead of lists. So a lot of the absento constraints in our relational interpreter represented that, or related to that, basically, and it's really annoying. The other question I have, and maybe this is more important, is one thing that makes the relational interpreter so slow, I think, is that we just have a very naive association list representation of the environment that takes a long time to look up variables. And I wonder if you could do any better here. Well, maybe you don't even need to worry about it. It may be that you don't have that level of overhead. So,
I guess it depends on how much you're relying on the logical operation to carry out your computations. So, for instance, in miniCurry, you rely less on the use of logic variables to, say, communicate values around. You can rely more on the straightforward functional evaluation results structure based on the trampoline thing I showed you above. So you rely less on logic variables to communicate things, so there might be less overhead in that sense. But eventually, you are still going to hit whatever overheads are present in your logical implementation, I think.
Gotcha.
Unless you write straightforward functional programs that make no use of the logic functionality.
Oh, okay, so I've got a question. For one thing we can do in the relational interpreter that's really cool is you really can put logic variables anywhere. So, for example, you can put it inside the code for append, right, and infer the missing code. Can you do that with this approach? Like, could you take your append definition and stick a logic variable in the code for append?
So not not in the same sense that you're thinking of. You could probably do something similar with at a sort of a macro level, in the sense that if you notice these run calls that I have here, these are the same run that you see in miniKanren. The only difference is that the specific goal that I'm using in this case is this denoted value, the same class status as a double equal in miniKanren. So what you would have to do to say, for instance, let's say I actually had inlined all the letrec definitions here, and I wanted to replace one like.
You're muted.
Sorry. Can you hear me now?
Yep.
I really have to fix that. So if you wanted to stick a logic variable representing code inside of here,
okay.
You would need to do it in some sort of indirect way. So for instance, you might need to somehow convince, you would have to say sequence something such that the code is actually bound to some actual code before it gets to the location of the interpreter. It's probably not going to have the same effect that you're thinking of. So it can't walk backwards, for instance.
Oh, okay. Gotcha. Okay. All right, well, I guess if you wrote an interpreter in this style, then you'd probably get that same behavior that we have.
Right, in that case, yeah, it would have the same status as the relational interpreter.
Yeah, I'd be curious to see how well it did. I mean, maybe in cases when you're running mostly forward, for example, I don't know if you would get benefit of the fact that you're writing it in the functional style, and maybe it'd be more efficient. That's what I'd hope. So yeah, I'd be very curious to see what the interpreter would feel like and act like in that setup.
Yeah, my hunch is that if you were running this, say, in a JavaScript implementation with the awesome JIT, that you actually might be able to get slightly better performance. Just because, say, V8, for instance, is amazing. I saw what it was doing with Veneer, and that was pretty impressive.
Okay. Yeah, it is very cool. It's like, I guess languages sort of don't outlive their initial reputations, or it's hard to outlive. So when Java first came out, it was very slow, especially with string stuff. And JavaScript came out, it was ridiculously slow, right? So I guess now I'm still trying to adjust my expectations of the speed of JavaScript. I mean, part of me still thinks of JavaScript as like the slowest language ever made, and that's just not true anymore. It's like actually the implementations have gotten remarkably fast. Yeah, and then of course the other big thing is the data structures, right? I mean, if you're using the right data structures, then even if your compiler is not as fast or just not as fast, you'll still win out once the programs become more complicated. I was definitely seeing that yesterday.
Right. I think you could probably do better for than the association list representation. You should be able to use immutable hashes with idempotent substitutions with a union find algorithm of some kind. I think you could make that work.
Well, Racket supports persistent hash maps and stuff like that. Are you using those, or are you just using association lists right now?
I am actually using Racket's built-in hash. Yeah.
Oh, okay, gotcha. So you're talking for the interpreter itself, the relational interpreter you're talking about, or are you talking about trying?
I was talking more generally about. So I'm actually using the hashes, but I haven't implemented a union find algorithm that can, say, produce idempotent substitutions and reduce the amount of variable indirection you get when you have chains of variables assigned to each other and stuff. I think so. I could still improve on my own representation.
That'd be really nice to see, because I know a number of people have tried Union Find with miniKanren, and no one's been able to make it run faster than the hash maps.
You said nobody was able to make it run faster?
That's correct.
So, oh, okay. So I'm probably thinking of something like Union Find, but actually still using the hash map. So, and producing a hash map as a result every time you perform a new unification.
Mm-hmm.
So I'll have to do an experiment with it, but yeah, I think you can make something work.
Orchid has a paper, persistent union find and scheme from an OCaml paper if you like. Yeah, so Orchid done some work on that. Daniel's done some work on that. Yeah, and then there's like so as you mentioned, the path compression, trying to reduce. Orchid's union find seems good for just logic variables. I'm not sure how you'd handle unifying a var with an atom. Yeah, so a number of people have played around with union find. I know Dan has played around with union find. Maybe we're just kind of dancing around the edge of what we need to do to make it really fast. But so far, I have yet to see a union find that performs better than the hash maps. I'm not saying it can't be done. I think maybe it can be done. It'd be very cool if it could be done. Daniel says
sorry.
Daniel says the OCaml paper uses a persistent vector structure. Okay. Go ahead.
I was thinking of a sort of a delayed path compression operation, where path compression would only happen upon access. So long paths could still be constructed as you're, say, constraining or unifying variables to one another. But as soon as you say, okay, I actually want to unify the value of this variable with something that requires a ground value, then suddenly path compression would kick in, cause all of the intermediate variables to be rebound to the ground value, and in that sense, producing an idempotent substitution at the same time, or partially idempotent relative to that use. Sort of amortizing the work involved to only when it's absolutely needed.
Yeah, Daniel says, my conceptual understanding is it implements path compression, basically like memoization, and the hard part is dealing with the side effects, the lookup. But yeah, Greg is describing basically what the OCaml paper is doing.
Oh, neat.
Okay, yeah, so I guess the OCaml paper that Orchid is referring to might be a good place to look. And Orchid's got some code on GitHub that comes from the paper, so that might be worth looking at it.
Cool.
All right. Very cool. Yeah. So faster variable lookup would be really, really helpful, obviously. Well, thank you very much, Greg. That was really interesting. I'd like to play around with that some, and of course, I would like to see how relational. I would like to see quines or I love you, or running append in a relational interpreter written in the style so you can put logic variables inside the code for append, or all those tricks that we're playing. If this turns out to be a more efficient way of doing that without losing any of the expressive power, I think that would be really cool.
Yeah, I think you should be able to define a self-interpreter pretty easily, and then you can run those experiments.
Yeah, definitely.
That'll be my next step, I think.
Very cool. Looking forward to what you come up with. All right, well, thank you very much. All right, wow, miniCurry. So I've seen a bunch of talks and read papers on curry and so forth, but haven't really played around with it in anger. So it was neat to see that. I've also started reading up on the constraint handling rules some more, and that also has this feeling of sort of combining term rewriting, functional programming, logic programming, all kind of together, and Curry kind of has that feel too. So it's interesting to see these different approaches that we've kind of underexplored, right? In miniKanren, we've sort of gone our own direction, which is interesting, but we haven't. Let's see. Hold on a second. See if I can scroll. Yeah, Danielle, my screen doesn't seem to be letting me do that. Hold on a second. Maybe I can do it. Oh, there we go. Yep. Cool. All right. Okay. Well, thank you very much, Craig. And I would say, now for something completely different, but this is actually kind of related to things we were talking about. In terms like doing things like making the relational interpreter faster and that kind of thing, and having more efficient representations of substitutions and all this sorts of stuff. Oh yeah, so Eugene says, seems that constraint handling rules can be easily implemented with condu. I don't know. Maybe, I mean, condu, the constraint handling rules mechanism, as I understand it, you have a constraint store, you're removing elements from the constraint store, moving them from one. You're doing like a bunch of term rewriting and things like that. So I think you can definitely do some of that stuff with condu. And it is a committed choice language. So yes, so we have a committed choice operator in miniKanren. And we support logic variables. So that's probably true. I mean, if it's all based on committed choice and logic variables, and we have committed choice and logic variables, then I guess we probably could implement CHR using condu. I hadn't really thought of it that way. That would be something interesting to play around with. Right now, I'm just kind of reading up on all the examples and trying to understand better the model. But that actually would be a fun thing to try. Would be to try to implement the constraint handling rules system in miniKanren using condu, which is this operator I normally don't use because it doesn't run backwards. But constraint handling rules also, is committed choice. So the idea is you can build up constraint systems that you can use in another language. So just like miniKanren is embedded in Racket or Scheme or Clojure or Python or whatever language, constraint handling rules can be built as a library in C or Prolog or Haskell. Apparently, their big success story, at least as of the writing of this book, was that CHR was being used in Haskell for implementing type systems, and that was their kind of thing that they were bragging about. So I didn't realize, I had thought it more of as a Prolog thing, but apparently the biggest success story is in Haskell, which I thought was very interesting. So I think they see themselves as kind of an embedded language. So I can imagine having an embedded CHR, having a CHR system for Scheme or for Racket or for Clojure or whatever, and then using the CHR system to build up the some of the constraints we use in miniKanren. Or as Eugene pointed out, I guess we could go the other way. We could use miniKanren as the embedded language and build CHR on top of miniKanren, which is something I hadn't really thought of, but I guess that would actually work. So, but some way of combining miniKanren and constraint handling rules and having them feed into each other. It would actually be really cool if we could implement constraint handling rules using miniKanren's condu, and then use the constraint handling rules to implement the rest of the constraints that we use in miniKanren. So you can implement finite domain constraints and all sorts of things inside of constraint handling rules. So that'd be really neat. That sounds like something worth playing with. All right. So the other thing I was playing around with, there are a couple of things we've been playing around with, but so one thing that one piece of feedback I've been getting with the relational interpreter, and I think this is warranted and good point, and is the relational interpreter has a couple of problems. So we've been writing these interpreters in a relational style for scheme and racket, and we've added pattern matching, and we support higher order functions and letrack, and we can do some interesting problems at this point. We can write them directly in racket or scheme and run them in the interpreter. But sort of two disadvantages we have. One is that the relational interpreter is quite slow. So if you write append in scheme and you run it in a relational scheme interpreter, if you just run it forward, that is the definition of append is fully ground, has no logic variables, and the call to append is ground, has no logic variables. You're just calling append on lists A, B, C, and D, E. And you can even say what the output is. The output list is A, B, C, D, E, right? So you have no logic variables at all in your program. It still runs really slow. It's like at least 10,000 or 30,000 times slower than just running it in scheme if your version of miniKanren doesn't have a smart representation of substitutions, right? And if you, like we were talking about a minute ago, if you have things like persistent hash maps or tries or whatever, maybe persistent union find, if we can get that working efficiently, path compression, which is a way of taking long chains of variables to values and then making that shorter. We can use some of those techniques, and we have implementations like Veneer that uses those techniques. Then the system becomes faster. But even with that, I see a big slowdown in the relational interpreter. So I started playing around with yesterday some ways to try to hand specialize the relational interpreter to make it run faster, and I can show you what I was playing with. I think it can be pushed a lot further. These are just kind of initial experiments to try to get some handle on how slow it was, or how we can start experimenting with some of these techniques. But I'd be happy to show you that. So that's one disadvantage, right? Is how slow the relational interpreter is, and the miniCurry thing that Greg was showing us is very interesting to me, because if you can, Curry combines functional and logic programming. And so, that's what we're trying to do with the relational interpreter, basically. That's another way to combine functional and logic programming. And if we could do it in a way that's way more efficient, but we don't lose any of the flexibility, we have remarkable flexibility with the relational interpreter, but it's very slow. So if we can try to change that trade-off so we're not paying that much cost, but we can still retain the flexibility, then that technique would become way more practical, and we could solve bigger, more interesting problems. That would be really neat. So that's one problem, is the speed. Another problem is, as people pointed out, we can only handle a subset of scheme, we can only handle a subset of racket. We're handling a Turing-complete, an interesting subset of racket, let's say, because we have a subset of the racket pattern matcher and all these things, but compared to the racket language itself, which is huge, racket is a gigantic language, we can only handle a tiny portion of it. And even compared to scheme, even compared to R5 or a scheme, which is not a very big language, we're only handling a small part of that. We know we can add setbang. We've done it. It has some serious performance implications and divergence implications. We know we can handle errors, explicit errors. That also has performance and divergence implications. We know we can handle code that's rewritten in continuation passing style, but as we mentioned before, one of the disadvantages of that is we lose some of the good behavior when running backwards in terms of divergence, cutting off infinite loops, and so forth. So we've got some problems like that I don't really know how to solve, and in some sense they may not be solvable with our approach. I'm not sure. We can run backwards in a sense just fine, but if you really want to prove that there is no answer when none exists, that's harder. So we can still run backwards, but if an answer doesn't exist, we can diverge. And if an answer does exist, we can't prune it sufficiently, so it could take longer to find it. What could we do as far as making the language bigger? Well, just take R5RS Scheme, which is sort of the old version of Scheme that I used for many years. I sort of still use that subset usually. Even for R5RS Scheme, there are lots of operators on numbers, right? Lots of arithmetic operators, which we don't handle numbers at all right now in the current version of the relational interpreter. That's another problem. And they're just like lots and lots of helpers. There's like things like kadar and catter and cateditor and all these helpers for accessing list elements and on and on and on. So I guess part of it is, well, what happens if we add 500 or 1,000 primitives to our interpreter, right? Part of the problem is even if the way we've written the interpreter right now, say we're making a call to catter, C-A-D-R, that's the car of the cdr of a list. If when we make a call to catter of some list, if our interpreter has like 1,000 different cases, then we could have this unfortunate circumstance where we end up having to try every single clause because it's a cond. We try every clause, right? Even though only one clause is of interest, and we can tell that immediately. So now there are ways around that. One approach is indexing, and David Nolan has added some form of indexing, I believe, to CoreLogic. I think David was the one who added that. And this is similar to the notion of indexing in databases, and I think many prologues have indexing systems. So the idea there is that when you know which clause you're going to try, there's no reason to try all of them. You should be able to immediately jump to that one. So we don't have indexing in miniKanren, and as far as I can tell, the indexing in CoreLogic only works on sort of database type stuff. I don't know if it works on arbitrary goals. But one of the things I did last night was try to play around with sort of hand encoding a form of tabling on the relational interpreter and sort of hand specializing things. So there are these ideas of partial evaluation, where you have a program and you know something about the input, so you can rewrite the program to take into account what you know. So that's another thing we could do. If given a certain query, we could rewrite the relational interpreter based on the input query to be more efficient, stuff like that. There are a bunch of techniques we could try, and basically we're not doing any of those. We're not doing anything that's smart. We're not doing abstract interpretation. We're not doing any analysis at runtime where we check to see which arguments are ground and using that to help reorder goals when we have multiple recursive calls. We're not doing anything like I think Daniel suggested where we're looking at the complexity of calls or any of that stuff. Okay, we're as stupid as we can be. So the fact that we can do anything interesting is kind of amazing at some point. But if we want to handle bigger problems, we want to handle a bigger subset of language, we're going to have to figure out how to make it faster, and we're going to have to figure out how to add new forms to the interpreter without paying a big overhead. If we double the number of forms we handle or primitives we handle in the interpreter, we don't want everything to become twice as slow or exponentially slow or whatever. We want to, certainly when we know what call we're making, we don't want to have to try every single clause in a cond. So that's what I was playing around with, and let me see if I can bring up what I got, and we can take a look at that. See what people think. All right. Let me share this. There we go. Cool. All right. I fixed up my Emacs, by the way, a little bit. I was very proud. I figured out how to make it yellow when I highlight something. Before it was black on black, which was not very readable. Okay, so let me see if I can show you some stuff I was playing around with. So I've got all these specialized versions of the interpreter. So first of all, let's just look at the interpreter, the relational interpreter that I've been playing around with Michael Valentine and Utah quite a bit. And here is our main clause, this eval expo thing. So, and we've looked at this before. We have an expression, we have an environment, we have a value, right? And we're creating this basically we have a three-place relationship between these three values, right? So if the expression, for example, is a quote expression, we're quoting some value like a symbol foo or something like that, then in this case the output of the quote foo will be foo itself. And we have these side conditions. We're saying that in this case, val can't contain closure, the tag closure. This is kind of an unfortunate artifact of the fact that we're representing closures as tagged lists instead of having a different data structure like a struct or anything like that. This is why Michael Valentine and I have been playing around with adding unification of bracket-style structs to miniKanren. But in any case, so this subcento really is kind of stupid and it shouldn't be here. This is just purely a side effect of the fact that we're not very smart in the data structures we handle. Another place where we're not very smart in the data structures we handle, as I've mentioned, is that our environments, if you look up top, you can see our environments in our lookup. Here, our environments are tagged lists, right? Or we could use association lists or whatever. In any case, our lookups are going to be linear in the length of the environment. And as the environment gets really long, it's going to take us longer and longer to look up a variable in the relational interpreter. So if we could have a more efficient implementation of the relational of an environment, that could also help. I don't know if we could easily do things like a tree-based, balanced tree-based, or trie-based, or a representation of environments. We'd have to figure out how we could do that in a way that miniKanren is constraint solving and unification would still work, and we can run everything backwards. But being able to handle smarter data structures in miniKanren itself. So we've been talking about adding things like persistent hash maps to the miniKanren's implementation and scheme or racket or whatever language closure. But having available to a user of miniKanren some sort of smarter data structure so they don't have to do linear lookups when they want to do something like a map. They don't have to use an association list, which is very inefficient. That would also be really cool. But once again, we have to figure out how can we write this in such a way that that they can still run programs backwards if they want to program in a relational style. So I don't really know an answer to that. I started thinking about it a little more. And sometimes maybe you have to trade off a little relationality for the performance. Maybe it turns out that what you're doing is a special case, and you only care. You only need a couple operations, so you don't need a fully general, fully relational version of a data structure. Maybe you're only doing a couple operations, and you can get away with a kind of a simplified version of your data structure. I don't know. But that's the subcento here on the closure is purely due to the fact that we're representing closures as tagged lists, and that's kind of a bummer. This is also a bummer right here, not an invo of quote and inv. And we've talked about this before, but the idea of this line of code is to say that we're allowing shadowing in our interpreter. Scheme allows shadowing, so you can shadow a variable. You can shadow quote. You can in scheme. You can write lambda, quote of foo, right? And this is not the same as lambda x quote of foo, right? So we've shadowed quote quote is no longer the built-in quote form and scheme. Now quote is just some function that we're passing in. So in order to support this behavior of scheme, we have to check when we're about to treat quote as an actual quote form built-in scheme that we're not shadowing. So that's why we have this not an invo call. And this is quite expensive. If you look at not an invo, you can see that it's recursive. We're recurring. Here's a recursion right here. In fact, in this case, it's pretty nasty because we have not in defso and not in info, and the defso is because we have letrack. So this is a very expensive operator. One approach to trying to make things faster is to just say, well, we're not going to be as general as scheme. We're not going to let you shadow build-ins, things like quote. Quote is always quote, and lots of languages do that. That's not very schemely, but we could take that approach. Another approach to try to figure out a different way, a more efficient way to tell when that quote's been shadowed, instead of looking down these long lists. So maybe we could keep an extra set around or something like that to tell very quickly. We don't care what quote's bound to in the environment. We just want to know if it's bound at all. So maybe we could do this more quickly. But it turns out that this not an invo is very expensive. This is a very expensive operator. So that's kind of annoying. So those are things that slow down the interpreter. Both the absento and this not an info slow down the interpreter quite a bit. And then if we just look in general, we've got all these cand clauses, especially when we come down to things like the primitives. So we have all these primitives. And if we look at the prim expo, so we have booleans, we have and, or, null, symbol, not, car, could'er, cons, equal, and if. And we could imagine adding, probably 100 or 200, or for supporting Racket, maybe 1,000 more of these things, right? I mean, there's all the arithmetic primitives. If we were to support vectors, if we stopped using vectors to represent variables, maybe we use a special struct to represent variables. We actually want to support the vector operations. We could add the vector operations. We could add all sorts of things. So, we could easily end up with a very huge list of primitive operators. And right now, that would be very inefficient because we have this cand. So that means that, say we have a call to or, okay? That's fine. We will try the or clause, but we will also try the Boolean case and the and case and the null case and the symbol case. We're going to try every single possibility. And if we have a call to or, then we're going to try doing this unification with and that will fail. But we still have to do the unification. And unifications, take some time. It's somewhat expensive operation. So, every time we make one of these calls, we're paying for the fact that we have all of these primitives. And the more primitives we have, the more expensive it is. So that's kind of a bummer. That's one reason. I mean, that's really why you have indexing, is so that you don't have to try all these cases. You can only try one of them. You can jump to the right case. So that's another thing that can make things slow. All right, so what are we going to do about this? What are some things we can do to try to speed up the system? Well, one thing we can try is specializing our interpreter a bit, and we can do the following. We can change your eval expo a little bit, and what we can do is we can project the expression coming in. So what project does is it takes any term in our language, basically any value in our language, and we're going to walk star it. So we're going to look up the value of the term in substitution or the constraint store and ground it as fully as possible. Anything that has a variable that's associated with the value in substitution, we're going to replace the variable with the value. So we're going to make this term as ground as we possibly can, and then we're going to let bind the term to to a lexical scheme variable, also called expr. Okay, so basically, this just lets us, every time we refer to expr, to have the most ground version of expr that we can get our hands on. Okay, because otherwise, expr could come in as just a fresh logic variable, even if expr were bound to, we're fully bound to a ground term that was like lambda xx or something like that. If the argument coming in is a logic variable, we can't really do anything with the logic variable in scheme itself. Okay, we have to look up the logic variable in the substitution, and that's what project does. Okay, so at this point, within the body of project, expr is fully walked. It's going to be as fully ground, or sorry, it's going to be as ground as we can make it. It might still contain logic variables. It might still be a logic variable, but just to make this a little more concrete. So say we have in our substitution x is bound to 5 and y is bound to the pair, or so to a list of x and 7, like that. So that's our substitution. Then if we were to project y, okay, and then we have some goal inside of the project, or some code inside of the project, that would be equivalent to saying let y be walk star of y in the current substitution. We have to get our hands on the substitution. And then run the goal, or run some code inside of that, run the body, let's call it. Run the body within this this let binding. So really, in order to get our hands on the substitution, we have to have something like lambda s, and then the body is being applied to s. It's actually something more like that. But anyway, in any case, the point is we can look up in the substitution whatever y is bound to. And in this case, y would be bound to, in the body, y would be bound in this case to not just the list x7. That's what we get if we just walked y, but since x is itself 5, we would get a fully ground term. We would get the list 5, 7. Okay, so inside of body, we could, when we refer to y, we're going to see the list 5, 7 instead of a logic variable. So that's why project can be useful for doing these sorts of specialization tasks. Okay, so we're projecting the expression coming in, and now the expression could still be a fresh logic variable. Maybe expr came in as a fresh logic variable, that's fine. Maybe we're running backwards, and this is our query variable q, let's say. But once we project expr, we will have gotten rid of any variable in expr that's bound to a value in the substitution or the constraint store. So that's as ground as we can get. And now we can just actually write some scheme code. We're perfectly allowed to write scheme code within the body of project as long as we always return a goal. Okay, so this is a little bit like what Greg was showing us before with the miniCurry. Now we're mixing some scheme code and some code to produce miniKanren goals. As long as each of our con clauses produces a miniKanren goal, this actually runs just fine. Now, of course, I'm not advocating that you write your code in this style, right? We write the relational interpreter normally in a much more abstract style, but I'm just trying to understand better what sort of hand optimizations could we do, and ultimately you'd want to have a compiler or a specializer or optimizer that would generate this code for you. So I'm basically hand compiling my code to try to make it more efficient. And the idea is that now that I've projected the expression, If I know, for example, that the expression is a Boolean value, like say that expr is a logic variable, it's passed in as a logic variable that happens to be bound in the substitution to hash t, well, I don't need to do any more work with the relational interpreter other than just to say that the output value has to unify with the input value. In fact, if I looked at val, I could project val as well. And if val is also a ground value, then I could just do an equality test to see if expr and val are the same. And if so, then just succeed, otherwise just fail. So I could even specialize this more if I wanted to. I could basically create a big table based on the values of expr and val, and maybe even inv if I wanted to. But the point is, if I know I have a Boolean, I can just do the single unification. I don't have to do this giant cond that has all these different clauses in it. I just go ahead and unify expr of val, the output with the val input. That's it, all there is to it. So so that's a nice thing, because I basically avoid doing all that giant cond and doing all the unifications and all that stuff, right? So I can limit the work of my relational interpreter just to a single unification in this case. And like I said before, if I look at val, I might not even have to do a full unification. I might be able to save on that a little bit, but probably I don't know how much more work I can save there. But basically I've eliminated having to do the cond and all these unifications. Similarly with number, if I know that expr is a ground number, I just unify it with the output value. If I know that expr is a ground symbol that represents a variable, I just have to do the variable lookup. I don't have to do anything else. There's no reason for me to be trying procedure applications or anything like that. Okay, so those are the cases where expr is fully ground and it's an atomic value, a Boolean, a number, or a symbol. I can basically just go immediately to the operation I care about. And notice that lookup-o itself, the call to lookup-o returns a goal. Okay, so every case has to return a goal. And then here's probably the most interesting case. So what if I have a partially evaluated expression, or partially ground expression, I mean, and it's a pair? So for example, maybe I'm making a call to cons, right? And I could either have ground values, like my expression is cons 3, 4, or maybe it's partially ground. Maybe it's, cons of E1, E2, where these are logic variables. Okay. The expression doesn't have to be fully ground. If that's my my expression, I can already tell that this is a call to cons. Okay. In fact, it could even be less ground than that. It could be .e star or something like that. I don't even have to know the length of the list at this point. I know that if it's going to actually work, I mean, if the interpreter is going to produce a value, that this has to be a call to cons. I do have to be a little careful, though, because of the shadowing, which I mentioned before. So there are two cases. Either this is a call to the primitive cons that's built in, and I'm going to get back a pair, okay, which is one of the two cases, or maybe we're inside, we're evaluating inside of a lambda cons, and we have a cons, okay. So maybe cons is shadowed. So either this call to cons is the primitive cons, or it's a shadowed cons, in which case cons is just regular procedure application. It's not a call to the built-in cons. And I have to handle both cases. So it's either just regular application, in this case, when I see cons, or if it's not being shadowed, then in that case I know I'm calling the primitive cons. Okay, and in order to tell the difference between these two, I need to check to see if cons is already in the environment of the interpreter, relational interpreter. If cons is in the environment of the relational interpreter, then we're shadowed, then we're in this case. We're in the context of some sort of binding form and cons happens to be bound already. So we're calling cons. So it means that we actually have a procedure call and something's being passed into the cons. Okay. So we can tell the difference between the cases of calling primitive cons versus just a regular procedure application to cons by telling whether or not the symbol cons is bound in the environment. Okay. But once again, we've eliminated most of the possibilities. We know that it's either going to be a regular procedure application or it's going to be the primitive cons. It's not going to be calls. We're not calling and. We're not dealing with symbols or numbers or booleans. We're not doing variable lookup in this case. So it's either the primitive cons or it's the regular application. Those are the only cases we could possibly have once we know what the car of the list is. That's a ground symbol. So we don't have to know the full structure to limit the number of possibilities we have. Okay. All right. So we have to handle the two cases: the regular application case and the primitive cons case. So the way we're going to do it is, first of all, we're going to try the regular application case. And this, the regular application case actually is a little more complicated because there are two types of application in our interpreter. We can either have closures that take a fixed number of arguments, or closures that take any number of arguments, which are called var args in Scheme. And we can see this closure right here takes any number of arguments. Wait, let's see which one is x. Yeah. This is the var args case here, where we have x as a symbol. So x can take any number of arguments, whereas down here with this x star case of the application, this closure takes a fixed number of arguments. It could take 10 arguments, or 7 arguments, or 0 arguments, but there's always a fixed number of arguments. So we have the interpreter broken down into two different types of application. Maybe it should be abstracted differently, I'm not sure. But so we're going to try each of those two types of application and see if that works. In order for this to work, it probably can be optimized some more, by the way. In order for either of these applications to work, cons has to be in the environment. You have to be able to look up cons and find that it's bound in the environment. So you could probably specialize these two cases and do the environment lookup first to make sure that the cons really is bound in the environment. Otherwise, there's no point. You know that these things these application cases can't succeed. So anyway, these are the two application cases, and we have to look at those. What's more interesting, and we were doing those cases anyway in the regular relational interpreter. Excuse me. The more interesting case is once we've tried these two applications, we're going to try a third cond clause, and that third cond clause is going to be kind of special. What we're going to do now is look at the operator that's in the car of the expression. So in our case, the car of the expression would be cons, the symbol cons. And first of all, we're going to check to make sure, we're going to verify that cons does not appear in the environment, because if it did, it would be shadowed. And now we're going to do a case on cons, or sorry, a case on the operator, which could be cons, it could be quote, it could be lambda, it could be whatever. And we're just going to jump immediately to the code for that one case. So if we have a cons, I think I've got, where's my cons? I should have one here. Okay, here's all the special cases. Here's my cons case. So if expression is partially ground and it's a list, and the first symbol in the list is cons, then I'm just going to do the work for cons. I'm not going to consider any of the other clauses in my interpreter. I'm not going to look at any of the other condi clauses. I don't need to. Now here I'm doing a unification with the expression. I don't know. I might be able to save a little work there because I already know something about the expression. I didn't bother trying that. But you can see there's another thing that I could probably take advantage of, and I'm not yet doing it. And this is what we talked about before. What I could also do is check, once I do this unification of the expression, if the first argument to cons is a fresh variable, but the second argument is ground, for example, I want to try these recursive calls in the opposite order. I want to recur on the ground term first, because that might immediately lead to failure. And then I want to recur on the fresh argument. So based on what I see from this unification, based on the values of A and D, I might want to reorder my clauses here. And so I could do that dynamically. I could check on the groundness. If A is a variable and D isn't a variable, I definitely want to reorder these calls here. And in fact, I want something more sophisticated. What I probably want is a little function that's going to tell me if A is more ground than D, or if D is more ground than A. If D is more ground than A, then I want to reorder these and do it in the opposite order. So that's something I could do at runtime, and that check might be, it'll cost a little bit computationally to do that check to see if D is more ground than A, but not a whole lot probably. And if I can cut off an infinite loop, that's a big win. So that's another optimization you could do. Hand specialization you could do is based on the instantiation, the groundness of A and D arguments. So there are other things like that we could almost certainly do once we start hand specializing the interpreter. And obviously some of these, if not all of these optimizations, we could write a compiler or optimizer for. Okay, so this is the case. We've got all these cases where we're making some sort of call to a primitive, or something built in like lambda or null or if or whatever. And if we're making a call and it's not one of the things we recognize and it's not a procedure call, then we just fail. So if you're calling, foo as a function call and foo is not bound in the environment, we want to fail, because that's what this clause is about. We could write this more efficiently probably than the unification, but that would work. Unification works for failure, unifying false and true. And then in this last case, the expression is still a fresh logic variable. We've walk-starred or projected the expr. It's still a fresh logic variable, has no structure whatsoever. Well, in that case, we can't play any of these tricks that we were playing above. We just have to try all the cases because we don't know anything about expr. However, we still could be using more information, because even though expr isn't bound, the expression coming into the interpreter is not bound, val, the output value, could be ground or partially ground. So we could do the same sort of trick that we were doing above with expr. We could be doing that sort of trick with val. So for example, if you know that the output value is a pair, then there's no reason to try the number case, because a number, when you evaluate a number, it's not going to give you back a pair. That sort of thing. So, if we had zero question mark is not going to give you a pair back when you call it. So we don't need that either. So we could take advantage of the value of the output val as well, not just the input expression. So by taking advantage of information about both the input expression and the output value, we should be able to cut down the branching factor quite a bit, and also do things like reorder the goals when we have multiple recursive calls to be in a better order that's going to be less likely to lead to divergence. Or if you look at a call for a procedure application, we've got a val expo, and a val expo. There's 3 different calls to a val expo in this procedure application, and it's not always clear what order those calls should come into. What order should those calls come in? If you know something about the groundness of the arguments coming into the interpreter, then you could make better choices about which order to use. Okay. Now, one obvious disadvantage, especially when writing this code by hand, is that we've exploded now. So now this file has just this evaluate part is up to 390. We got the specialized stuff, 390 out of 9. Okay, so So it's about 300 lines of code for our val expo now because we've got all this redundancy and stuff like that. And obviously, if we wanted to add special casing on val as well, it's going to be even more complicated. Okay, so this is really something you want some support for. You want an optimizer to generate this code. But it turns out we can avoid the branching factor and so forth. Now, this projection is a little expensive, especially since in this version of miniKanren I'm using just a naive association list representation for my environments, for my substitutions in miniKanren. So looking up a variable can be quite expensive, but I only have to do the projection once at the very beginning. Each of these unifications, unfortunately, also is going to do a walk, but if expr is already ground, that walk is basically a no walk. It's really fast. Okay, so I've got all of this specialized code, and well, let's see how we did. We can try running a few of these examples. So I'm just trying a very simple expression, which is just trying to run append forward. So let's look append. So this is append using letrec, and I guess this isn't completely ground, right? So our logic variable is still, our output variable is not completely ground. We should have another version that makes this ground. Maybe that would run faster. Let's try this. So instead of having a query variable, we can have something like this. So now we have no logic variables at all in this expression. Okay, we're just running everything forward. In fact, that doesn't even have to be a letrec, but that doesn't matter so much. Okay, so let's try running this version. See how fast or slow it is. So there's more specialized performance. Be embarrassed to tell you how many hours I spent last night playing with this, but it's actually kind of a fun game to play. Okay, so the first call to append, it took 42 milliseconds and so forth. The second one, interestingly, even though we gave a completely grounded list as the output of the evaluator, took a little bit longer. There's a fair amount of variance between the runs, so I think it's roughly the same. Okay, and then we start getting to longer lists. So now this append has, the first list to append is actually fairly long, and we can see now we're up to 2.5 seconds. Okay, now I think a lot of that is just based on how slow this version of miniKanren is, because we're not using a smart version of the substitutions. When I ran this in Veneer, David's implementation, it did much better. I think it was like 200 milliseconds or something like that. But you can see that we're running append forward, and it's taking 2.5 seconds. Let me just take the scheme code, because we're just running scheme code, and let me time the scheme code. 0 milliseconds and 400 bytes allocated versus 2.5 seconds and 15 megabytes allocated, right? 15 megabytes versus 400 bytes, that's not so good. Not so good at all. So that's sort of where we're starting. Okay, and let me rename this. So this is, I guess this is the original. This is the unoptimized, I guess, unspecialized. Yeah. Oh no, so this is more specialized. Ooh, uh-oh. That's not good. That's the more specialized? Wow. Okay, well, let's go to the unspecialized version then. I thought that was actually the fast version, or the slow version. thing is going to be pretty grim with the slow version then. Let me grab that. We've got the unspecialized version as well. Let's see how this does. So if you remember, it was taking us, I think, 40 milliseconds for the first one. And this one, let's see, we were taking 42 milliseconds versus 100 some. Okay, and we had 2.5 seconds for the last one. And here's 11 seconds. Okay. Yeah, so what's happening here is that we're getting 11 seconds and 50 megabytes for the unspecialized version versus like 15 milliseconds and 2.5 seconds for the specialized version. That's not so great, but it's still, the specialized version is doing better. So we're doing, we're using about 3 times less memory, and it's running on the order of 5 times faster, 4 times faster. Once again, some of these results are skewed by the fact that we're using such a dumb implementation of our substitution. So when we run these in Veneer, well, if we run the unspecialized version in Veneer, it gets a lot faster. It's not nearly as bad as 11 seconds. Veneer doesn't support project, I don't believe. So we could actually do some level of specialization just by projecting the variables, so that that's sort of like a type of path compression where you don't have to keep looking up, you don't have to keep walking the variable over and over again once you do that. So that even just having project might make things a little faster. In fact, that's probably something worth trying. But so that's my feature request for David, is to do a version of Veneer or expose something like project in Veneer, just so we can try that out. Okay, thank you. In fact, okay, so that's we can look at a couple other things. In fact, I do have some benchmarks here. Where's my performance? Let's look at. I had some notes here in one of my buffers. It's not here. Yeah. Okay. Okay. So here are some comments I had from playing around last night. Yeah. So I started making longer and longer lists, and this is with the unspecialized interpreter. But once the list started getting fairly long, this was taking 30 seconds to run, and was taking 91 megabytes to run for a fully grounded version of append. Okay, so this is taking 30 seconds to do these appendings of the list. Now, part of it is because of the dumb version of substitution. So in Vicari, this takes 0 milliseconds to run, just in straight scheme. When I was running these in Veneer, it was way faster, even though I was using a curried Y Combinator version of append. I was running this kind of horrendous-looking thing. I was still able to do this in like 171 milliseconds instead of like 30 seconds. Okay, so in Veneer, it's way faster because the data structures are smarter. The representation of the substitution's so much better. Still, you're comparing 171 milliseconds to 0 milliseconds, and that's not so great. Orchid asks, does it grow linearly? It doesn't seem to grow linearly when you don't have a smart data structure. It seems worse than linear. With the smart data structure, I'm not sure. That'd be nice to chart it out and see how it grows. But what I would like to do is, so first of all, one thing that this clearly shows is you have to have a good implementation of the underlying substitution data structures. Otherwise, it doesn't matter what you're doing with hand specialization. It doesn't matter how clever you are writing your miniKanren code. You're just going to lose because the substitution is going to grow large, and then you're just not going to be able to handle these things efficiently. So you absolutely need a better version of the substitution, a better representation of substitution. The reason we have historically used association lists is just from more of a pedagogical standpoint. You know, it's easy to implement association lists and play with those. It's easy to teach people how to use those. Things like persistent hash maps and so forth. The underlying data structures can get kind of complicated. So if you're just trying to show someone the ideas, it's not so good. Maybe, I don't know. But in terms of actually getting any sort of performance, you really do need those data structures. It's just way too slow. So, you know, Veneer for this example is already, you know, something like 150 times faster than the microKanren version for this particular query. And it's still, however, at least 170 times slower than Scheme, probably way more than that, because basically I couldn't get microKanren to go above 0 milliseconds with any reasonable list I could type. I'd have to generate some really long lists. So, it's still way slower in under the relational interpreter, even with the smarter data structures, than it is in Scheme. But in some sense, it shouldn't. There's no need for it to be so slow, and this maybe ties into some of the Curry stuff that we were seeing earlier from Greg. Because this is just Scheme code we're running, we should be able to specialize this a lot. And in fact, to some extent, we might even be able to just have like a Scheme interpreter just run it directly, or even call a val in some cases, and just try to leverage the fact that this is just a functional program. There's no reason for us to pay huge overhead if we don't have to. So, it was somewhat distressing to me that my code was 30,000 times slower than the Scheme code for that one query. So we can definitely do better, and Veneer definitely does better. But I would like to start playing around more with, well, what happens when we start specializing the relational interpreter inside of Veneer, or inside of microKanren with a smarter data structure representation, or inside of the version that Greg has that's using persistent data structures. So we should be able to do a lot better. And I'd be curious to see how much we could limit the overhead, at least when things are ground. Now, when you have logic variables in the picture, then obviously you can't do all these tricks. But a lot of the time, we are doing things where we have one logic variable. When we're running these queries in a relational interpreter, obviously, a lot of times we put one logic variable one place in the code, and we want to see how fast it goes. In that case, still most of our code is probably still ground, and for those sub-expressions, we shouldn't be paying gigantic overhead, or be unfortunate if we had to pay gigantic overhead. Let's see. Shouldn't miniKanren be the baseline rather than Scheme itself? Yeah, Orchid. I think either miniKanren. So also just Condi. Just the Appendo version. Appendo in miniKanren. Once again, it was really hard for me to get it to go above 0 milliseconds. Like Appendo already in miniKanren is already really fast. So Appendo is quite fast. Append in a Scheme interpreter in Scheme, yes, that would also be a better comparison, and I should try benchmarking that. I also suspect we're paying fast overhead, but to be fair, if we did a Scheme interpreter where the environment representation in the Scheme interpreter is just an association list, we might find that at some point it starts getting kind of slow because of the recursive calls and the environment growing and that sort of thing. So that's another thing I should try is just doing it in a regular Scheme interpreter and seeing what sort of performance we have. Eugene, this unfortunately implies that good miniKanren code needs to be specialized, which means we lose expressiveness of miniKanren. Yes, I agree that we want to automatically specialize. We don't want to do this stuff by hand, right? What I'm trying to figure out is, if we were to specialize, how much of a benefit would we get? And just trying to start thinking about how should we think about comparing these. And so these are good questions that you all bring up, like, how should we compare the performance? Should we compare it to a scheme interpreter? Should we compare it to Appendo? Are both of those sort of unfair or misleading? I mean, they're kind of both misleading, but certainly Appendo and running it in Scheme are both, many orders of magnitude faster than what we're getting with the relational interpreter. So I think we have there's a lot of slack we could kind of get rid of. I don't know how much we can get rid of, but a language like microKanren that's doing automatic specialization. In microKanren, you're actually compiling the different variants of the relational code to functions, and then at runtime, you're picking which version of the function to call. Now, obviously, if you have logic variables or partially ground arguments in all the positions, then it becomes much trickier, and I don't think microKanren handles that, or it doesn't handle it very well. So I don't know we can do that, but in cases where we have sub-expressions where we're purely running it forward, where it's really just fully ground scheme expression, feels like we should be able to do better. There are a bunch of other optimizations we could potentially try, but and then there are also things like back-jumping search that Michael Ballantyne's been working on, and other things like that. But I'm just trying to start thinking about how we could start playing with the relational interpreter and try to start erasing some of the overhead, because it's factor of 30,000 isn't so good. Now, obviously, part of that is just I need a better version of miniKanren that I'm using in practice that's using the trie representation or something like that, or I need to just move to Racket and use the persistent data structures. But I am very curious how much faster we could make the relational interpreter. It's like, I guess this comes down to, if we can make the relational interpreter 100 times faster, right, or 1,000 times faster, something like that, then we could, or a different complexity class, then we could start handling much bigger, much more interesting problems, and also through things like that specialization, where we can dispatch directly to the individual case if we know some information about the code. That could also allow us to safely scale up the amount of the language we handle or the number of primitives we handle without sort of getting ruinous performance. Have you experimented at all with the staging that Jason showed? No. So Jason Heeman and Dan Friedman, they gave a talk at Lambda Lounge, or was it? No, it was Lambda Jam in Chicago a couple years ago, showing how you could specialize an interpreter. And well, actually, sorry, I think I take it back, David. I think I did play with that a little bit, or at least looked at it. The idea is that in their case, you could pass in the expression at a different time than you pass in the environment, and that if you know the expression up front, you can partially compile things. So so you can specialize the interpreter if you know the expression under evaluation, but you don't yet know the environment, I think it was. I played around with that a little bit, but I think that was before we really got into the new relational interpreter stuff, where we're running just scheme code inside the relational interpreter. So that's another place we could specialize things, right? We could try specializing the scheme code under interpretation. We could try specializing the relational interpreter. We could try improving miniKanren. I think there are lots of places where we could do some partial evaluation or specialization. I'm not sure what gives us the most bang for the buck initially. So part of it is I'm just trying to figure out in practice, how fast might we expect this to go, right? If we want to make these techniques more useful and be able to handle bigger, more interesting problems, we're going to have to find ways to make it go faster. And I think part of the problem is right now we have a bunch of individual techniques, but we have it's like for each implementation, like backjumping. Backjumping works for one version of miniKanren, but that version of miniKanren doesn't have all the constraints. Or and in fact, I think that version of miniKanren only works with the naive substitution representation. And the full constraints, the full constraints are cool, but the version of full constraints I'm using uses a dumb version of the substitution, and so we've got all of these different versions of miniKanren that are kind of in different states, but we don't have like a super uber version that combines all of the modern constraints and all of the nice search techniques and all of the data structure representations and the nice reification and everything else. Like we don't have something that also has the back jumping search and where you can parameterize the search and so forth. So I think part of that is just kind of an engineering effort trying to build up something, and also related to that is, and maybe this is where constraint handling rules would come in. At least the version of miniKanren I tend to use is actually pretty stupid when it comes to solving constraints. Like it tends to look at the same constraints over and over and over again. So maybe something like one thing that we could do is let me end the screen sharing here. Oh yeah. So there's like attributed variables. There's the constraint handling rules. There are all sorts of ways we could potentially do the constraint solving much more efficiently, where we're not looking at the same constraints over and over and over again. Because right now, once something gets added to the constraint store, at least in the versions that I've implemented or worked on, you end up checking those constraints over and over again and solving them again many, many times. Like, even when you're doing operations that have nothing to do with constraints, so it's not very efficient. So I think, I guess the good news is I think there are lots of ways to make it more efficient. I guess the bad news or less good news is that there's just like a lot of engineering effort in order to do so. But I do think we can make miniKanren much faster, the constraint solving much faster, the search much faster. Make the relational interpreter faster, make it, do automatic specialization and all these other tricks. Having the relational interpreter itself be able to have a smarter representation of the environment would be a huge win potentially, instead of just an association list or tag list internally. So I don't know how to do that. I don't know what the right way to do that is. So, something like, can we implement a try in miniKanren, or can we implement it's like a persistent hash map in miniKanren? I don't know. Can we add, persistent hash map constraints to miniKanren and still make it relational? I don't know. So those are sorts of things that would be useful. I mean, even adding sets is tricky, it seems. But having set constraints would let us do things like figure out if a variable is bound more quickly without having to go through the full substitution, potentially, or through the full environment, and that could speed things up. Oh yeah. So the other thing I noticed. Okay, so I did find when if I got rid of the shadowing in the relational interpreter, that made a big difference. If we didn't have to check for shadowing and we didn't have to do the application case, if when we see a call to cons, like that really is a call to cons, it's not potentially a shadowed cons in an application, that speeds things up a lot. So that's another thing to consider. Is like, well, maybe we either want to disallow shadowing, even though we lose some flexibility, lose some schemeliness, or maybe we want to have something like ShaScheme or Vicari or many of these systems. They have like primitive built-in notions. Like, in ShaScheme, there's a primitive cons that you can call directly, and the macros expand to and whatever. And that's like honest to goodness cons. That's the built-in cons, and so potentially we could have a notion of having a difference between the built-in cons versus a cons that might be shadowed. So I don't know. That's kind of a trade-off in expressivity and language you want to model and so forth. But anyway, that's what I'm starting to think about, and so that's one reason I was really interested in the miniCurry stuff, is I would like to see how miniCurry would do with some of the relational interpreter things we want want to play with. And if it turns out that the miniKanren relational interpreter is like 1,000 times faster, that would be of great interest to me. I'd like to see what sort of things we could try with it. Could we solve really big problems? I don't know. But yeah, right now I gotta do something to make the version I have much faster. So one thing I'll probably do is try adding the try implementation that Aziz Ghalom had back to the current implementation of miniKanren I use. The other thing is the constraints solving is not so great in our current version. I don't know how the veneer version is doing in that department. The try thing, yeah, so there's Aziz Ghalom created a try implementation of substitutions based on, I guess, one of the algorithms in the purely functional data structure book. And the idea is that every time you create a variable with a fresh, the variable is assigned a number. There's a counter, and just increment the counter. And the binary representation of that number tells you whether or not to go left or right in the try for doing a lookup. So it's basically just this automatically self-balancing tree, radix tree or whatever you want to call it. It gives you logarithmic lookup and all those sorts of nice properties. So it's purely functional. So that is an implementation I might maybe go back to and play with that. The association list stuff is maybe good for teaching. Has I guess its trade-offs even for that, but for trying to work on bigger problems, it's just way too slow. Is the code online? I don't know if it's online yet, but I thought it was somewhere. But I was trying to look for it the other day. I'm not sure if it's online or not, but I'm hoping. Let me put it this way: if I can get the try version working, I'll happily put it back on. I will put it on my GitHub because that will be the version I'll want to use. So hopefully I can get to that in the next couple days and speed that up. So, but as far as the constraint solving, also I'm curious to see if any of your implementations of the constraint solving for things like Absento constraints or for any of the constraints we have are a little more smart. Because right now, we're not doing attributed variables, we're not doing constraint handling rules. Basically every single time we do a unification, we have to go back and solve the constraints again. That's really slow. Eugene says, if you implement a try, take a look at RBB try. We could implement lists using that. Then appendo will be very fast when specialized with RRB try. I think last time there was a link to Cameron Swords had some sort of RRB try, right? Maybe that was in Racket, something like that. Yeah, I should take a look at that. I think so the try stuff already works, and I already have a version of miniKanren that works with the tries that Aziz helped cook up. He did all the try stuff. I shouldn't say he helped cook up; he cooked it up. But the thing is, once you start getting into some of the constraints, you have to change. So disequality constraints are the big one, right? So if you do a disequality constraints and you're not using the association list, if you want to do the way we do constraint solving for disequality, then you still have to keep track of a prefix of the substitution. So you just have to keep that as a separate argument. So I don't think it's I don't think it's a particularly hard thing to do, but just got to sit down and do it. Relaxed radix balanced tree. Okay. I have a separate prefix as part of my substitutions. Yeah. Yeah. So I think that's the way people have been implementing it for disequality constraints. Is that you just have a you just do like a little extra bookkeeping, right? You have an extra argument that's growing. So that's not hard to do, but it's just I just have to modify things. So you can't just like swap in the try for an association list or whatever it is, and then have it all work. You have to change the constraint handling a little bit, but it's not too much work. So I just need to sit down and do that. So I'm hoping to do that this week. Yeah, and let's see this RBB thing. Let me bring that up. Yeah. So, yeah, someone had mentioned this last time. Racket RRB tree implementation, yeah. And you know, I think to a large extent it doesn't matter. It doesn't matter so much what representation you use. You know, there's even a paper that Dave Bender and Lindsay Cooper and I worked on with Dan showing different persistent data structures you can use to represent substitutions. And there is some difference between them, but the main thing is, you know, the big difference is between not using them at all and using one of them, right? Yeah. I guess a staged miniKanren wouldn't work, like meta or camel. Staged in what way? I mean, in some sense, I think the miniCurry is sort of like a staged miniKanren. So we can do manual specialization easily. I don't know. I haven't really looked at meta or camel, so maybe that would work. I don't know. I mean, ultimately, what I'd like to figure out are what specializations work well and then automate them. But if we had to manually do them, we could do that way too. So, excuse me. You know, one thing that would be very interesting is looking at things like, you know, the cons example where depending on the groundness of the arguments, there's a clear choice on which recursive call you want to take first, right? Now, there are other ways to solve it, to solve that problem, like backjumping search can solve that, or the concurrent conjunction can solve that problem. They all have different trade-offs and different costs, right? Just because MK isn't applicative like Curry is, we can't really put staging annotations in. Yeah, well, I mean, this another thing we could do is have like a real miniKanren compiler, right? I mean, miniKanren is typically an embedding, but we could do like a compiler just for miniKanren that just knows about miniKanren. I mean, that's what David was doing, I think, right? Where you can have annotations, you can have modes, you can have whatever, and you know, unifications can compile down to pattern matching when we know something about the groundness and stuff like that. David says we could use the same Prolog specialization tricks, though. I think the main issue is being able to pick out individual Condi clauses in the first place. Yeah, and I don't know if we could steal some of the indexing techniques also. You know, obviously my hand indexing is okay, but you know, there may be way more efficient ways to do that. I don't know. So anyway, I'm just trying to figure out. I know how bad the performance can be. Let me put it that way. And now I'm just trying to figure out, okay, if we're willing to do some, you know, go through a little bit of engineering effort, how much of that can we get back? And then sort of what's the way forward towards doing more aggressive optimization? And you know, obviously there's decades of experience in Prolog systems for doing this, and Mercury has a really good story. Curry's got an interesting story, you know. So what can we do to try to reduce this overhead of, you know, probably at least several hundred times? My guess is more than that. But you're right. I should also go back and just try it with a scheme interpreter to try to better understand how much overhead we're really paying. Maybe a lot of it is just making the relational interpreter use better data structures, you know, stuff like that. And those are things that maybe specialization can't help with. You know, using the right data structures helps a lot, right? So maybe we need special constraints for representing the substitution of things like that that lets us. I mean, if we really had good set constraints, we could use sets to represent. Or if we had like a hash map, relational hash map constraint, we could use that to represent the environment, and that could be really efficient. I don't know. I'm not sure how to do that. I've never seen relational hash maps in any logic programming system. Maybe they exist, maybe they don't. Let's see. Orchid, I think there are loads of choice points left around. Prolog can avoid a few choice points that miniKanren can't by inspecting the heads. Yeah, that's right. And there's also, Oleg had this headlet macro for original Kanren that basically did a form of projection and then let down the variables to be just regular lexical variables. We could try going back to that too. That also could probably save a lot of work. Greg says something like the finite domain constraints. Yeah, I mean, maybe something like that. I'm not sure. I don't know what form they would take, but some smarter representation of environments in the relational interpreter would be really cool. Another approach would be to just go for a language that doesn't have variables and doesn't have variable binding and doesn't have lookup. So there are things like concatenative languages like Forth. Forth itself seems to cause some problems just with the structure of the programs in terms of running backwards. But the idea of getting rid of variables, there's things like combinatorial logic. Some of these approaches don't seem to have enough structure though to cut off the search. So you're gonna when you're not gonna have any answers. So I don't know. Maybe So maybe part of it is like maybe scheme is kind of annoying just because it has variable binding in the way it does. I'm not sure. Regarding hash maps and sets, yeah, something maybe like the finite domain constraints. I don't know. Are you suggesting maybe using the finite domain constraints? Could we use the finite domain constraints directly as? Well, there's also things like De Broglie notation, right? There are things like De Broglie notation. Yeah, so I guess if you use De Broglie notation, or you use, if we assume, or if we use, maybe nominal logic programming would also help us with some of these things, with shadowing issues. So, the shadowing issue maybe we can handle more elegantly. That's very expensive, the way we handle shadowing right now. It's extremely expensive. And then, of course, there are other issues like handling setbang, because as soon as we thread something monadically through the system, we lose the ability to reorder goals in certain cases, and that can have performance and divergence implications as well. So I don't know if there's anything we can do with monadic stuff to make that more efficient. But anyway, specialization, trying to understand what techniques we can use, all those sorts of things I'd like to explore more. And also, of course, I'd like to see more what miniCurry can do. It'd be really cool to have a mini-Mercury, right? Mini-Mercury would be neat to see, can we take a relation and compile it down to a bunch of functions that would run just like a scheme functions, that would run just as fast as normal scheme functions. And I don't know, maybe to some extent that's what the miniCurry gives you. But it feels like we should be able to do way better than we are. Let me just put it that way. It feels like we should be able to do better, way better than we are. So, okay. Well, we're 3 hours in, so I think probably good time to call it. Thanks everyone for joining us, and thank you, Greg, for showing off the miniCurry. That was really neat. I'd like to play around with that, and definitely I'd like to see what a relational interpreter looks like in that system. So I'm going to go ahead and stop the broadcast. Everyone have a good week. Thank you.